Hi everyone, my name is Edmond Apiedo Danso, a member of Group 5, and I welcome you to this presentation on cache mapping. Today, we will dive into a concept that significantly impacts processor performance in modern day computers. I hereby present to you our topic of interest today. We'll be looking at cache mapping, associative and bank memory, fully associative cache mapping, and then direct cache mapping. I'm humbled to introduce to you my group members. We have Adi Mark, Azikojo Asari, Kuma Jerry, and then myself, Edmond Apiedu Danso. But first, what is cache mapping? And then why is it important? Why is it necessary? So before we can understand the techniques, cache mapping properly, and then how to apply them in computer architecture, let's first understand what cache is. So what is cache? I'm taking you straight to a kitchen. We'll use that as a scenario to understand what cache is. So imagine a busy chef. The pantry, which represents the main memory here, holds all ingredients, but accessing them takes time. The chef has a prep area, which is the cache, near the cooking station for frequently used items like chopped onions. This cache allows for quicker access during cooking. Similarly, in a practical sense, a computer processor has a small fast memory called a cache that stores frequently accessed data and then instructions from the slower main memory. This cache significantly improves processor performance by reducing access time to frequently used informations. So now, why cache mapping? So let's understand why it is cache mapping we are applying and not another techniques. Okay, so the main memory is divided into phase block size, while the cache is divided into cache lines. Cache mapping determines how a specific memory block gets placed into a cache line. This mapping strategy is crucial for efficiency, cache utilization, and overall system performance. Here, let's look at the techniques involved in cache mapping. We have the direct mapping, the fully associative mapping, and then the set associative mapping. Without wasting much time, let's understand how they are being applied. With a direct map cache, it is simple and efficient for small caches, but can lead to conflict if multiple blocks map to the same line. Associative cache. It offers more flexibility but requires additional hardware for comparison during cache access. With a set associated cache, a balance between the two providing some flexibility while maintaining what efficiency. We will take an intro and then look at least one of them for now before the rest of my group members will take you to the rest. We are looking at the direct cache mapping. Let's check an example on it. So as you can see, that's a pictorial and architectural representation of how a direct map is being used. So here, see, imagine a small cache with 4 lines. As you can see, there are 4 lines there. Each memory block has an index, as the pictorial is showing there, that determines its corresponding cache line. This mapping is straightforward but can lead to conflicts. For example, if two frequently used blocks have the same index, one might get evicted, causing performance slowdown. More on the direct cache mapping. In direct map cache, each address location in main memory maps to a single location in cache memory. Since main memory is much larger than cache memory, there are many addresses in main memory that map to the same location in cache memory. So in summary, what is cache mapping? Cache mapping is a vital concept in computer architecture. By understanding different mapping techniques like the direct map, the associative and the set associative, we can appreciate the trade-offs between simplicity, flexibility, and performance. Thank you. The rest of my group members will take you through the rest. Please stay with us, stay tuned, and then you understand more of our concept. Thank you again.
Hi, I'm Ademark, a member of Group 5, and I'll be presenting on fully associative cache mapping. So before we dive in, we know from the previous presentation what cache mapping is, and we talked about it being the way or how or the technique data is sent from the main memory to the cache memory for the CPU to access for processing. I'll be talking about one of the three types of cache mapping, which is fully associative mapping, like I said earlier. So what is fully associative cache mapping? This refers to a technique of cache mapping that allows mapping of the main memory block to a freely available cache line. What this means is when the data is sent from the main memory using this fully associative cache mapping technique, it will save itself on a free line, unused space on the cache memory. It doesn't compile itself on a space where there's already a data. So with this technique, every data from the main memory saves itself in a fresh line on the cache memory. That's how this works. So let me explain on how it actually works. The cache uses a tag field to store the memory address. So it uses the tag field. It doesn't use the index bit. The index bit tells the data where and the location on the particular place you should save. But with this technique, only the tag is used, and the tag can save any data on any fresh line on the cache line. So with this, the data can save anywhere on the cache memory. So it searches for only a free space. When it's occupied, it moves to the next line. When it's occupied, it moves to the next line until it finds a free space. Then it saves itself. Since it's not having a particular place to save itself, it can save anywhere it wants. Let's talk about the advantage. The primary advantage of a fully associative mapping is that the conflict mess issue is resolved and the hit rate is increased. Well, this is simple to explain. When we say the hit rate in computer architecture, this simply refers to when a CPU is searching for a particular data and it finds it in the cache memory. It's a hit because it got what it wants in the cache memory. So it's simply a hit. But when we say it's a miss, it means it didn't get the data it's searching for in the cache memory. It has to go to the main memory or any other secondary memory to search for that information or that data. So this will be a miss. But with this technique, the data are organized in separate lines. So the CPU easily finds or gets access to a data, and it prevents a miss because it doesn't have to go through one line and search for a particular data like it does in the direct cache mapping technique. Well, so this will also prevent the hit rate. Let's talk about the disadvantage. On the other hand, the primary disadvantage of the is that the comparison time is increased because every data is in its simple or in a new line. So let's assume we have a 12 entry cache. So assuming the data is on the last one, the last line, so it has to go through every single block of every single line to search for its tag bit before it gets to it. So it makes it it increase the time for searching for a data. To summarize everything, this type of mapping is more complex and requires more hardware to implement, but it provides the most efficient use of cache space because it stores data from other memories in an individual block, making it accessible. So to summarize from all what we said, we know that this type of mapping is more complex and it requires more hardware to implement. But it provides the most efficient use of cache space. This is because it stores the data from other memories in an individual block, making it accessible faster. This prevents misses, and that's all we need. When there's misses, when there's no misses, it means the data is got faster, and this makes everything move smoothly and neatly. Thank you.